All right. Hope everyone's ready to get back to dealing with slides, and I hope that the demos were useful. I know I said I was going to upload those. I didn't really get a chance to clean up my code. And I was also trying to do some video editing so that I could get my screen and the audio together. Um, that I wasn't able to preview it. Maybe I'm doing something dumb because I don't really know how to do video editing stuff. It was taking like an hour and a half, 2 hours to render, so I didn't get a chance to look at the final result of doing all of that. Um, I also know that I'm a little bit behind on grading homework too. I've looked at all the code. It's just a written part, and that I handed over to the new grader that I got. I'll check in with her. I'll probably ask her to show up at class just so you guys can all put a face to the idea of us having a grader. Um, and yeah, so homework 2 grades should be out kind of soon, sometime this week. I'm aiming to do it tomorrow. Uh, project, did I give you guys feedback on the newest report that you submitted? I did not. Huh. Okay. Yeah, I'll definitely bump that up on my priority list. Uh, what else? Project homework. Oh, quizzes. Yeah. So we're done with 3 so far. Um, 2 more. I'm probably not gonna do one this week because I think I haven't uploaded my last slides, have I? For what was it? Instant segmentation and all of that. Did it? Is it? Whatever. I'll check later. That and there's 2 more homework assignments that we got to do, and we're coming down to like the last what is it, 3-4 weeks, I think. I don't want to leave that stuff all the way up to the end, so expect homework. I'm gonna try to formulate it and have my solution tested and ready tomorrow, so that I can get it out maybe tomorrow night and give you a week or 10 days, depending on how involved the process of coming up with a solution is for me. Uh, um, I have a couple of ideas. I'm thinking I'll have you guys do um, like phase key point detection using something deep learning based, and then you warp, um, I don't know, some template transparent image and do like rudimentary Snapchat face filters. Um, Either that or that there was something else that I was thinking of that I can't remember right now. I think it was like, oh yeah, actually, I'll probably have you guys do that one later, like a gesture-based mouse interaction thing where you like track your hand, estimate hand pose, and maybe doing something like that as a click, because then that would involve things like hand pose estimation, first of all, and camera calibration, maybe. I don't know. I'll probably have you guys do that one last. Um, Phase key points. I think that that would be a good way to sort of solidify interacting with deep learning models and doing something with what it predicts when it's more complicated than class labels. Okay, so for today, some of you might have caught a peek of what today's lecture is about when I had stuff on the wrong monitor. We're going to talk about vision language models. The first, I'd say like 60% of what we're going to talk about today, it's not immediately obvious why we should care about all of that, because a lot of these are concepts that have more to do with natural language processing than the image domain. So we'll hopefully by the time we get to the end of it, things will make sense. But before getting into all of that, just a quick recap of all of the things that we know so far. This is the way we've been motivating everything that we've talked about in class so far, which is that the idea is to extract meaning from a visual representation of a scene, of an environment, whatever. The first steps that we took towards extracting meaning was involving things that you could infer from pixel values and their distributions in a very rudimentary form. We had edges and corners and things like that. Then we moved on to features that were a bit more sophisticated, like SIFT and SURF and HOG, which use things like the orientations of gradients. Then we decided to just let the data figure out what features are best for the problem that we're trying to solve. We did that by throwing images into convolutional neural networks and letting them learn weights that sort of correspond to filters being derived from the set of images that it's exposed to, and that enabled us to solve problems where you would have to classify an image, or we now have the ability to detect objects and sort of separate them from everything else around it. We can tell objects, we can tell what classes, we can tell locations, but does that really tell us meaning? I mean, you could say it tells you something about what's in the image, but it's not really enough to consider it a description. So how do what's a step in the direction of getting descriptions of images? As always, a good data set does a lot to drive a field forward. So it turns out the COCO data set that we looked at for instant segmentation also had captions. And these were just descriptions of the images that the people who annotated the segmentation masks and stuff put in. If you recall how these data sets were built, it was done using Amazon Mechanical Turk, which just assigns a bunch of images to random people who get paid to annotate. And they wrote a bunch of these descriptions. And maybe we can do something with descriptions and images now that we have both of those. So you could say that detection and segmentation, you're looking at patterns of pixels, kind of like the deformable parts models intuition, where we care about the distribution of pixel values relative to each other. But to get from that to captions is kind of a leap. We need some way to bridge the two spaces of text descriptions and pixel values. So we're going to build towards understanding how we can represent meaning within text in the context of a usable neural network pipeline. So the first difference when dealing with images and text, text has a temporal aspect. I hate to be that kind of instructor, but at the back, if you guys could keep it down. Excuse me. You're throwing my flow off. It's distracting, and it's hard for me to figure out what to say next. If it's important, you can step out, speak, and then get back in. I really don't have a problem with that. Just, yeah, okay, back to it. The first key difference is that when we're dealing with images, all the information that you need to make some sort of inference or prediction about it is within that one frame. Whereas with text, if you think of what one unit of meaning is, it's typically correlated with words and whatever punctuation you're using, and the sequence in which they show up, that matters. So you can say that there's a temporal aspect to it where the order in which the words appear really dictate meaning. So we sort of need to have that context of what's before and after a word that we're looking at, in addition to just the meaning of the word that we're looking at. And we need to adapt that for neural networks. So this, a lot of this content, as usual, Dr. Redmond's, who is a Star Wars fan. This, I mean, I'm pretty sure you guys know what the word is. That should be in the blank, which got a little shifted. That's my bad. What's the word? Yeah. So we're able to tell that the word over there should be galaxy based on the context of the words that are around it. Now, to do that with neural networks, or just understanding meaning from language in general, not even constrained to neural networks, that just happens to be the way that we do it. So that's the context in which we're talking about it. To formulate the problem, you could say that, well, given a sequence of words, you want to predict what the next word in that sequence would be. And the first problem to deal with is encoding, because as we've been seeing in every lecture so far, neural networks, any computation, really, we need numbers. We can't operate directly on strings because this doesn't mean anything to a computer, really. So based on what people found when they were trying to figure out effective representations for words, the finding was that it takes about 3,000 words to cover about 95% of common text. And if we try to encode that the way we were encoding our class labels, or say doing one-hot encoding, which is you treat each of the 3,000 words as one class and then one-hot encode that, and then you want strings that are 6 words long, then that's a vector space that's 18,000 elements. And again, that scales with the number of words that you want in your string. So not a great way to go about doing that. one-hot encoding is inherently sparse because there's only one in it and everything else is zero. So if it's one word in your 6-word sequence, each of those will have 2,999 zeros, and it's kind of wasteful. So one of the initial ideas with dealing with the temporal aspect was called a recurrent neural network. And the key to it is in the name recurrent. So the idea is to handle sequential data, you would take one token, which can either be a word, a character. When you're doing things like speech to text, they're divided into syllables. So whatever one small unit of text is, we treat that as a token. And then given a token and a simple feed-forward model, you predict another token. The thing to note here is that there's this connection between each of these blocks, and the output that you get from the first one gets passed in to the hidden layer of the next one. So you're adding context of what's around the token that you're looking at. And doing that, you could hypothesize that you'd be able to predict what should come after that. And each time you do that, along with producing output, so then your memory for this will include the prediction. The good thing about it is we're able to do this independently for each token, and it's no longer a time-dependent idea where you don't need everything that came before, but you're only taking one token and the token that came before that, and you're holding on to the previous outputs. Now, how does this input affect the memory? How does the previous state affect the current one? And given input memory, what output do we predict? The way that is formulated, this is not all that different from the forward pass logic that we've been seeing so far, where you have a set of weights, you have an input at time t, or position in the sequence, and there's an activation function that goes with it. And then this term over here is the hidden state of the previous string in the sequence, the previous token in the sequence. And there's a set of weights for that state, the previous state, because there's a weight update happening every time you're doing this forward pass, predicting something, and then you propagate backwards. So there's naturally two sets of weights, one for each state that we're considering, the current one and the previous state. And that is your prediction for a forward pass. The output and current memory will have the same values because the output in this step gets used as the memory for the next step. W is dealing with the current state, so it takes the input, updates memory. V is the set of weights from the previous state, and that is part of the process of updating the this gets updated to W, and then phi is some activation function. It's kind of a lot to keep track of. so many sets of weights, especially since it wouldn't scale very well because the larger your model gets, the more weights you have to keep track of. So in practice, what we do instead of that is we just have one block with one set of weights, and we unroll that a whole bunch of times, and we compute the forward pass for all of those in a single step. So if this would be a 3-word sequence, 3-token sequence that each goes into a recurrent block, and then the forward pass operation predicts one output corresponding to that input, which also gets passed into the next block along with that block's input, and then that generates a prediction, and then this gets passed into the next one, and so on. So this is simpler to compute, fewer things to keep track of. And this works because it's just one block that we're able to unroll for predetermined number of times. It's an arbitrary number of times that you unroll it, and once you get past that amount, you would just shift the sequence of tokens that are plugging into the model by however many times they're unrolling this, and plug that in for the next pass. So there's a couple of things to pay attention to, and that will help build intuition on why we care about meaning and context of neighboring words. So if you think about the word time, you can either think of it as a noun or a verb. If someone's, let's say, running track and you time them, that's thinking of time as a verb. And then there's a long time ago where it's a noun. So if you see the word long before time, then you can probably guess that the context in which the word time is being used. And there's also an interesting case over here where you have the word far, and the prediction over there that we should see is far for this particular string. And there's another far, and after that we see the word away. So it's the same word but different predictions, and those are again informed by what is in the memory. There's one of the caveats with trying to do it like this is that every time we're computing memory from scratch rather than holding on to things long term, since memory only considers the state of the block that was immediately before it, and the farther away you go, the less the contribution of this would be, since there's so many updates leading up to getting here. So instead of updating the entire memory vector, which, yeah. Yes, the weights of the hidden layer, you can think of that as a representation of the input, because in a simple feed-forward model with just one layer, what you're doing is you're taking your input and projecting it to some, if there's 512 neurons in that layer, you're projecting it to a 512 dimensional space. You can think of it like that. It will become clearer when we get to embeddings, which will come up after this, but they're just weights that are sort of like a meaningful hash of your input. And yeah, so since they're weights, it's a vector, and the idea over here is rather than updating all of them, we only update a few of them that would require the most change, which will in turn allow us to hold on to some of the more important things from earlier and only change the ones that would be most affected by whatever new token we just see. The first approach that implemented this gating logic to address the long and short-term memory differences and handling those differently was the LSTM, which stands for long short-term memory. That it's not really used much anymore, and it's pretty complicated. So while I will bring that up, we won't go into that in a lot of detail. Instead, we'll talk about gated recurrent units, or GRUs. And these came out after LSTMs, but these are simpler than LSTMs. And these are still used to a large extent. So this is more relevant to talk about. And it's a really busy diagram with seemingly a lot going on. It's not scary, really, when you think about it in terms of gates, which I'll do now. Basically, the yellow blocks are just single layers with some activation function on it, and they're called certain types of gates. And depending on what those layers are designed to do, we make some inferences about whether to hold on to some part of the state or whether to update it, whether to discard it. So h of t minus 1 is the hidden state for the previous token. This is the current hidden state, which is predicted and passed on to another block if there's one after it. And it's also the prediction for that token. And then there's all of this stuff in there, and xt is our input. So the overall abstract steps that happen within here is you first look at both the memory, which is the previous hidden state, look at the current input, and based on those two things, we decide what part of the previous hidden state is important. And informed by the context of the current input, we decide what parts are important and what to update. And then we calculate that update and decide what parts of memory to keep and update. And the output is a weighted sum of the old memory, the update, and what positions to keep. And this will get clear once we understand what the gates are. So there's a reset gate, there's an update gate. That's the reset gate over there. This is the update gate. The reset gate, so this is not standard terminology to call it a mask, but I feel like that helps me visualize what's going on. So I took the liberty of saying that the reset gate basically generates a mask of positions to discard, which will then get applied to the previous hidden state. So kind of like a segmentation mask of a person, and everything that's not a person, you do something to it for for the background blurring example that we worked through, similar concept. Everything that would be true in this generated mask from the reset gate, only those positions you would discard, or conversely, the complement of that mask is what you would prefer to hold on to. And then the update gate tells you what to add to the new state. So that gets applied to this. And you'll see there's a tilde over the H there. So this is a candidate hidden state, a candidate prediction, which would be a whole vector. So if your hidden layer size, let's say it's 128, your candidate prediction would also be of that same length, but then you apply another mask to it that says which of those should be kept, sort of. And then applying all of these masks, we also, there's this step where you take the complement of this should be the update mask, and apply that to the hidden state also. So a lot going on. The update gate takes the previous state, generates a mask, determines how much of the previous hidden state should be retained versus updated, uses the current input and the previous state, and spits out a vector of values between 0 and 1. And if it's closer to 1, then you want to discard those. If it's closer to 0, you want to keep those. Oh, wait, this is the update gate. So it's the other way around here. In the reset gate, if it's closer to 1, you would discard those. Oh, I think I have these switched. I'll have to go back and check. But regardless, that's just implementational details. The overarching concept is that there's two sets of masks that tell us how much of previous state to keep and what parts of candidate predictions we hold on to. So at this point, we have a couple of masks and a candidate prediction. And so the final hidden state is just a weighted sum of previous hidden state and the candidate state. And that is informed by the masks. So a very quick summary of what each of those gates gives is that your reset gate has vector positions. It's a vector of positions and whether to keep them or not within the state. And then the update gate tells you how much should come from the old state and how much should come from the candidate state. And then when you put all of that together, that becomes kind of evident from how we're formulating what's going on, because there's, let's see, complement of the update gates output is applied to the previous state. This is directly applied to the candidate state, and both of these coefficients add up to 1. So you're basically blending the previous state and the candidate state to get your final one. Candidate state is an activation function applied to a weighted sum of previous state, the reset gate mask, and the current input. So this is positional relationship within the state vector that determines which positions of this to keep and discard. and those are the masks. So working backwards, I think it's a bit easier to understand what's going on with the previous state and the current state. That gets applied to the current one, and this gets applied to the previous one. So putting all of that together, we have our update rule, which lets us calculate one forward pass for one of these blocks, and then we stack a whole bunch of these together. LSTMs have a bit more going on. The way they formulate the gates is a bit different. So instead of one update gate, basically there's an input gate and an output gate, I believe. Yeah, I'm not going to go into this, and this is not going to be on any quizzes or whatever, but just this is the source of the idea that led to gated recurrent units being a thing, which is why it's up there. So using that, we're able to analyze sequences of words and formulate our approach that predicts the next word given a sequence. Now, if you think of the problem of translating text, it's you basically, again, have a sequence that gets encoded into some format, which is the state of each block or memory. And then you want to decode that into its corresponding word in a different language from that same latent space. So you can think of this also in encoder-decoder terms, kind of like how we thought of the UNet autoencoder style architecture with CNNs. That is an encoded representation that we've learned, which projects it to latent space, and then we take that set of values and then have a decoder block with a different set of weights that accepts that same representation and decodes it into the corresponding string with the same meaning. So we'd have one set of weights for each language to project it to the same meaning space. Now, since we're dealing with that sort of representation where, actually, let me skip ahead a couple of slides to, yeah, this sort of thing is what we saw with UNet, and I don't want you guys to pay attention to any of the notation over there, but basically you have your sequence of words which gets projected to a latent space, and that's just a vector representation of your input, and that then gets decoded. So we can also represent images the same way, because that's what we did with the UNet when we were doing segmentation. We were encoding them to just singular vectors and then decoding that back up into our segmentation masks that we were predicting. So it's the same principle. We extract features, progressively distilling them, composing them into more complex features, until we end up at a single vector that describes the whole image. And when you have that representation, you can then plug it into a decoder, which can spit out text token embeddings. Some samples of predictions that we get for captioning. These are some of the better ones that are close to what you would expect for what's in the image, or they're correct, I guess you would say, even if it's not how you would necessarily describe the image. And it's not a very robust approach, but it was the best way to do it for quite a while, up until like transformers became a thing. It's around 2018, I believe. And there's cases where the predictions don't really make any sense. So we should be able to do better, but to do that, we need to understand why, how we can explain the cases where it doesn't perform all that well. Ultimately, since we're only looking at words that are immediately next to the tokens that we care about, and those influence the prediction a lot more than all the other tokens, it's kind of like doing a nearest neighbor approach to the problem. And the only reason those did as well as they did was because of how much data we had. So there were a lot of examples for it to learn from, and it was able to, it was hard to overfit, basically. The other aspect that we've talked about when we were talking about image problems was, how do you know how good your predictions are? And with images, it's, I'd say, a bit easier to just conceptualize how to score something, because if you're dealing with object locations, then, well, you're able to supply those locations as your ground truth. And estimating how good or bad they are is just a matter of seeing how far away the predicted location is from the ground truth location. And distance is easily computed, right? But for a caption, that there's a lot more nuance, and there's no straightforward way for getting something like a distance metric. There were a couple of automated scoring approaches. The BlueScore, Meteor Score, those were seen a fair bit, but they get saturated really quick, and it's hard to squeeze more out of that approach. So another problem that we would like to be able to solve is, given an image and a question with it, we want an answer to the question that is informed by the image. Is that harder than captioning? This arguably requires you to actually understand what's going on within the image, even beyond just what objects are in it, or for this particular case, you would need to know what a mustache is, where you would typically find a mustache, that there's another object there which is made of something that is not hair, and that they're bananas. So there's a lot going on. Here, we'd need to know that, first of all, there's a child, that the child is sitting. Sitting is usually associated with something that you sit on. So there's all of these complexities to understand. How did that come back there? A step towards that is the idea of embeddings, which I just touched on briefly, but basically it's a distilled representation of whatever is in the image, right? Based on what features we have. And ideally, we'd hope that it also encodes some of the other meaning information, like sitting involving a chair or a place to sit on, and mustache being made of hair. And to try to have a hidden layer of the size of a language vocabulary would be kind of impractical. 3,000 words would still only cover like 95% of words that you commonly see. It's non-trivial computationally. So Word2Vec was an approach that had a bunch of embeddings pre-trained, and it was a single layer neural network with a hidden layer much smaller than 3,000 words. And this was able to predict these basically had good representations of tokens that could be used to predict the next word. And since it's in that format, it's also something that we can then apply our standard optimization kind of approach to it. What I talked about earlier, projecting it to a higher dimensional space, this is kind of what it looks like, where depending on the meaning and the context that you're trying to capture, there's these implicit axes along which each token is placed in that space, and the embedding is a representation of the coordinates in that space. And the cool thing is that we're able to do things like this. Since it's a vector representation, you can compare distance by subtracting the two vectors. So once you apply this to a large corpus of text, it would, you'd naturally see Madrid a lot more around near the word Spain than you would see Madrid near Italy. And there's also is it the capital? I don't know. Geography is not my strong suit, but Madrid is to Spain as Rome is to Italy is something that basically gets encapsulated in that representation. And oh yeah, they are capitals that should have paid more attention while making these. And also the aspect of whether it's a verb or a noun or tenses, that those would be nearby, and there's a transform that you can apply to one tense. If you know the direction to move in, you'd be able to find the corresponding past tense from that. Now this, just to help visualize what's going on, this I picked up from 3 Blue 1 Brown. I really encourage watching his Transformers series and Attention and stuff if this seems a bit baffling, because Attention, it's taken me a long time to wrap my head around the fact that this is even possible to encode something into just a single vector and also have it somehow represent complex meaning. So embeddings, each word is however many dimensional vector, and each of these represents the contribution of some parameter, which will be a bit more evident in a while, but basically these all get plotted to a higher dimensional space, and where they are in that space can be used to do things with it and tell things about each token. Now, typically, this is not how tokens are divided, because there's also punctuation to deal with and tenses and things like that. But this is a motivating example of the couple of kind of things that we are able to do with this embedding representation. So the word king would be at some arbitrary place in this space, which is again a composite of some other attributes. So a king is a person that will contribute to where this vector location points to. The king also implies, let's say, power or wealth. So all of those would also be implicitly part of that. Then there's lived in Scotland. So whatever the embedding for Scotland on its own would be, a king who lived in Scotland would be closer to where Scotland is in that space than just king on its own. So we're able to add this embedding to this to move it and get a king who lived in Scotland. And then there's murdered, predecessor. Those would also get added to this, which then moves their vector further down, and then in Shakespearean language. So that's a description of this sentence, the word king in this sentence, because all of these are attributes of the sentence that we're looking at. Another example, we have the word mole used in 3 contexts. There's the mass that we see in tissue, there's the chemical quantity descriptor, and there's the animal. Now, an embedding, if we're starting out with something like this, Word2Vec, you would typically use this by first training it on a corpus, and then you freeze the weights and just use that to generate these embeddings every time, right? So the set of numbers that you would see for the word mole would be the same every time. And we need to encode context into it to differentiate what the word mole means in these sentences. The normal neural network way is how the embeddings are generated in the Word2Vec approach, where we distill it using fixed weights. Each layer has an activation applied to it. But we also want to inform our representation with context. And attention was a mechanism that was proposed to solve this problem, and it's at the heart of a lot of what we use today. There's a few terms here that come from this isn't the kind of terminology that we've been seeing so far, because everything that we've dealt with so far has either been in like signal processing terms or linear algebra terms. But queries, keys, and values, this where does it fit into all of this? That's a bit less approachable, I think. At least it was for me, because I don't really databases and all of that, not something I cared for particularly. But the idea is that for each query, we match it with keys and then return a weighted sum of values based off of how close a match the query is to the key. And this is how the whole thing is represented, where we take the query and key, apply a softmax to the product, and then multiply that, use that to influence the value predicted in a way that reflects contribution of each of those queries and keys. What that means is that once we have our embedding representation for each token, we're also able to encode how each token is related to all the other tokens that we're looking at. And to understand what the word mole means within context of the information around it, carbon dioxide, both of those are the biggest clues for what the word mole might mean. So we're able to take mole, we're able to take Avogadro's number, the embedding for that, and sort of shift it to get this meaning for the word mole, informed by the embeddings for carbon dioxide. There's self-attention, which uses a feed-forward network after it. So you take your sequence of tokens, put it through a self-attention operation that looks up token keys in the dictionary generated by all the input words, which is your embedding space that you train your word-to-vec kind of embedding generator on, or your encoder. And then there's the encoding, which gets modified based on context. So Fluffy has this exemplary embedding that maximizes fluffiness, and there's blue, which maximizes blueness, and then you combine them and you get an embedding for fluffy and blue together. Bird and forest together give you an embedding that represents that idea. And the queries can be thought of as just operations that you would use to tease out context, which are again represented as more vectors, and keys. The query key space is where you would represent your queries and keys, and then using that, we're able to find embeddings corresponding to queries. It's hard to wrap your head around. It was for me, it still is a little bit, but just from being exposed to the idea repeatedly, I've learned to sort of accept that the idea of high dimensional latent spaces encoding meaning is a thing. Definitely watch the 3 blue 1 brown explanation, especially if you're a visual learner. But basically what goes on, so we generate both keys and queries for each token, and multiply them, which gives us sort of how well it matches with every other token that we care about. And then that is a measure of relevance, or that is what we call the attention score for that token. So the correlation of verdant and forest verdant describes forest. So you treat each of these as a query and each of these as a key, and see how well they relate to each other. And that gives you the relationship of every token with every other token and how important they are to representing the meaning. And since we have this whole, if there's n tokens that we're looking at, the attention space over here is n squared. So we want to distill that back down to n. And we do that by applying the softmax to it to find which of the tokens is most related to the other token. And the way to train this is sort of implicit. We basically just hide one of these words. The dog barks. You would mask dog and replace it with just a mask token, which is a placeholder token for nothing. And with that as input, you would try to predict what word goes over there because you already know what sentence was there. We can just take existing, what's the plural for corpus? Is it corpi? I'm not sure. Corpuses, corpi of text. You already know what all the text is in there, so you just mask some of it and then use what you know as ground truth, use the masked one as your input, and learn to predict the right one, and let the attention part figure out the relationships between them as part of the optimization process. And that idea of attention is the heart of transformers and everything built on that. Multi-head attention is basically multiple self-attention modules that are run in parallel, and each of them has a different set of weights. And these are, the way these are used today is we use them to get good embeddings, basically. That's what we care about, the space of meaning into which all of this is encoded. And using that representation, we're able to solve a whole bunch of tasks. Translation, I guess, was the first use case that led to transformers and attention sort of catching on and people seeing a lot of promise in how that works. This is an attention map of what correlates with what other token. Now, the reason we care about all of this is, I mean, we spoke about captioning. So this should already be a bit evident what we're heading towards. But most of these ideas are from the natural language processing domain, and we're adapting it for the image domain by borrowing the idea of using embeddings to represent meaning, and then applying that to images and using attention also in the image space by tokenizing our images. So that that was introduced in the Vision Transformer paper, where basically you chop up your image into a bunch of patches and then use those as your words to then build embeddings of. And what all of that finally gave us is this joint embedding space where you have text and you have images that are paired, and we learn how to embed both of those into the same space. And that models meaning really well enough that you can take a text prompt and generate an image. So this was introduced along with OpenAI's DALL-E. And Clip is used on its own also for a lot more than just generating images with DALL-E, but that was the first use case that it was proposed in the context of. So yeah, this is the big idea. Jointly encoding language and image into the same space lets us encode really sophisticated understanding into just vectors of numbers. And we can take that encoding and then decode it. You can encode an image and decode the embedding to get a caption. You can do the opposite to generate an image. Question answering is also possible because of how embedding spaces work, where you can apply embedding to other embeddings to move them to a spot that fuses the information from both of them. And this is what has pushed the envelope beyond what was possible with CNNs. How much of this made sense? I'd say about, for me, if I was seeing this for the first time, I would want to get at least about 40%. Because it's not intuitive, especially if you're used to thinking in terms of images and pixels. How do you go from that to numbers meaning things? The way I was able to reason about it is similar to the example of Fluffy Blue, where you think of them as axes that represent a bunch of attributes like fluffiness and blueness, and combining them gives you a description of how much each of those axes contribute to the final token that you're thinking of. And yeah, we'll this is pretty much where the foundations of what we're doing today. I won't say that it's where it ends. That's a poor choice of words, but attention's the last important building block to understanding what goes on under the hood in everything that we've been using in the past like year or so, since these really took off and became commonplace household name sort of things. Yeah, that's it for today. I honestly thought this was going to take a bit longer, which is why I felt the need to rush through it a little bit. If there's any part that anyone wants me to go back to and maybe spend some more time on, I can do that. Or yeah, or you're free to leave. Question? Sorry?
How you say it's kind of like the homeworks due?
There's no homework due yet.
Yeah,
I was talking about, um, well, I said I had started creating homework two. I looked at all the code. Homework two written part, our creator Hima is creating those, and then homework three I will be creating and putting out sometime between tomorrow and Saturday.
Okay, I just want to make sure because I haven't seen any updates.
No, I didn't
online.
post anything yet.
Yeah, okay, I just want to make sure.
Yeah.
Thank you. Like, I'm just trying to understand the schedule for the homeworks because you said there are two homeworks and one project. Like this going to be like deadline each week or something, and there's an exam.
Yeah, homework, I'm leaning towards not having a written part because the problem solving aspect, I don't, I don't know. How many weeks do we have left? Let me check. So we are 20.
4 weeks.
Yeah, so if it's 4 weeks, I quizzes, I mean, I don't make the quizzes very hard. I don't think that they're hard. So that as long as you have intuitive understanding of the concepts in class, you'd be okay with. Um, so two more quizzes, two more homeworks. Homework, I'm leaning towards not having a written part and only having a code part because my main objective in terms of what I want you guys to take away from the class is being able to do the things that we talk about. And there will obviously be skeleton code and all of that, and it's only the core logic to be implemented. I'll keep the time constraint in mind. And I also know you're working on your project, so I don't want to leave them for like the last week.
Just the question that you said, like the homework that you're planning was with either segmentation or like key point detection. So would that include like training on model or like
No, just use a pre-trained model or hard cascades or whatever. Because before this, what I was thinking was last week, I think last weekend, I was working on skeleton code. I mean, I start with the solution and then trim it to a skeleton. I was trying to have you guys build a music visualizer that sort of analyzes the sentiment and emotion of the text and also the um, energy and mood of the music independently and then combine that and generate some sort of visualization. But I think that would be too involved, especially for a homework, which is why I abandoned that. And so the panorama homework, that is a very standard computer vision homework. And one of the downsides of giving something that is very standard is that um, even if you guys don't talk to each other, if you put any of that on ChatGPT or whatever, you all end up getting the same solutions. And I wanted something that's not out there, which is why it's taking me a while to formulate. And also something that has some subjective aspect to it, so everyone's outputs look different. So if you're doing like Snapchat filters for the face, then the choice of what object to put on the face, I'll leave that up to you. So hopefully everyone's looks different. um, yeah, and I won't have you guys doing a lot of heavy lifting for that, but just the goal of this homework would be to be able to interact with and integrate a pre-trained deep learning model in a way that you can do something with it, like the background blurring thing. It should be a quick process that doesn't involve a lot of computation, but it exposes you to the workflow of integrating a deep learning based approach. Yeah.
Can I sign the sheet? I missed the bus.
I remember what time you came in. You came in like close to 9:45. I don't remember.
I came early like 35, but I just sat in the last.
Okay. Oh, you need a, yeah. How's it going with the project for you guys? I remember yours. I just remember that you made good progress.
I changed the project because subject directions were now I changed it and made the report again.
Oh, right. You
Changed what you said. I think
what's your project idea now?
now it's finding menus and finding dishes and thinking about like finding nearby locations and finding the ingredients and everything.
Okay. Can you describe that a little bit more? So what's your input? A picture of food? Okay, and
Location, your location, and it takes you to when you take a picture and it takes the dish and then it takes you to all the go through all the dishes that it has in the model. Then it finds the nearby locations as those things.
locations as in
Like,
where you
find-
can like,
find the
oh, okay.
dishes.
No, just tell me about just the vision problems that you're solving. So you have food. What are you doing to that? Are you classifying it? Are you running object detection, segmentation? What are you doing?
Object detection, uh,
I'm not like it's not an exam or anything. I just want to understand the workflow. So um, you do object detection that tells you where some food item is and what kind of food item it is. What do you do with that information?
and then it finds takes the data from like Google Maps or other things, and it finds the nearest location where you can find the food or
That's still functionally no different from doing real-time object detection, right? Because in terms of vision tasks that you're solving, you're just applying object detection and that's it. Beyond that, it's just an HTTP GET request, right? You know a Google Maps search URL and just plug in class names separated by pluses, and that's it. how much of this do you have done so far?
Like started like I calculated the data, then now like as my report one is like also the data. So I started again and then I even took like 2 of my like late days and was working on it. It's so it was like a little bit hard to plan on the reasons. Yeah, getting it down.
See, we only have a month to go,
I'll
and th this is a graduate class. So, um, again, my goal is not to um give you a hard time. My goal is to have you complete the class in a way that by the time you're done with it, you're confident that given a problem statement, or if you come up with an idea to build something, that you'd be able to do it. So, the key to that is being able to think of these tasks that we solve as tools in your belt, that if you want to build a chair, then you'll need a saw, a screwdriver, screws, and then you'd be able to build it, right? So just how to think of them as tools that you can combine to solve a problem. So what I'd like you to do is, in addition to object detection, if you still want to hold on to that, think of what else you can do with that. Um, and I have my office hours tomorrow, 10:30 on Zoom. The link is somewhere on Piazza or Ubilance or whatever. I want you to show up and tell me. The more ideas you have, the easier it'll be for you to walk away with one that is acceptable. But for the sake of your own grade and how much you take away from it, I'd like you to take that seriously. Um, I mean, end of the day, it doesn't really like hurt me personally. It doesn't affect me even if you don't uh, put in um, work. And if you have other stuff that's making it hard for you to focus on this, then if you, I don't know, just like whatever problems you face, if you talk to me, then we can figure out a way to deal with that, right? And well, if you're okay with that amount of complexity, then you're an adult and you're free to make that choice. I can't force you to do anything you don't want to. Um, it's just that I just want you to understand that I'm here to help, and I'm also a student, and uh, all of this is very relatable for me because I've also gone through the same process. I know what the workload is like. Uh, yeah, and just the feeling of building something, seeing it work, and knowing that you built that it's pretty cool. It stays with you, and that really lets you. It's empowering when you're on the job once you graduate, just to know that something that you saw as very challenging before doing it is now something that you know you have done. That's all. Just think about it a little bit. Just even if you don't know how to solve a problem, if you just have an idea, we can figure out a pipeline to solve it together. I try to ask people about what their other interests are, like if you care about sports or playing an instrument or whatever. We can design something around that, but we're short on time, so just
show up on the office hours.
yeah.
Yeah, for the number plate detection, until easy OCR, we're able to track the number plate, get that text out of it.
Hmm.
The problem is like the filtering while we're doing that. Like some kind of filtering we are doing regarding the number plate format,
Hmm.
the number plate, how many numbers, alphabets would be there. But for different videos, we are getting a different format. So we are thinking like we have to stick to a particular video to
Filtering, what's the objective of filtering?
filtering. As I mean, once the text is extracted,
Yeah.
the easy OCR, we are like planning to save it in kind of CSV or something, or maybe
Uh-huh.
further speed detection. We are thinking we haven't thought how to do that. But for the format to be correct, we were doing some kind of formatting, like it has to be 67 digits, first through 2, 3 alphabets, 2, 3 should
Okay,
be
so that is to deal with cases where
where there are like
your
It's-
detected text is not very accurate
Accurate,
to
yeah.
what the actual text
Yeah.
is, and to smooth that sort of.
correct.
Okay.
And to apply the filters, we have to stick to a particular video. Like we got 2, 3 videos, okay, for the camera, which is recording the number plate and the
Mm.
cars. But everyone has a different format. So when
Mm.
you write, I mean, okay, we are able to handle the 2 videos. It will be having some different formats, so we can write separate conditions for that. But then,
Mm.
what about the general case? So
So when you think about it, in terms of who would use this, if it is to be implemented by some government body, then typically it would be constrained to
That is-
whichever country
you're
it's
saying
being used in. So if you can find a data set that has only videos from one country, then that sort of implicitly guarantees that the format will be more consistent. That's one thing you can do.
okay, we can stick to a particular video. You're saying that is having a specific format. Okay. I mean, okay, this is our model, which will be
Not one video necessarily. Your solution should be generalizable to different lighting conditions and stuff, but the you can constrain your problem by enforcing that format consistency. It should still work in multiple photometric conditions.
Yeah, that we're thinking how to do further. Like we're able to create the number of plates after that, to track the speed, track the vehicle, something like that.
Hmm.
Yeah.